Okay, let's go ahead and draw Lewis structures and 3D and describe Vespro and molecular shapes, and then tell me if they're going to mix with water or not. So, let's start off with 3 electrons for the aluminum and 7 times 3 electrons for the chlorine. So 24 electrons to deal with. Who do you want to put in the middle?
Aluminum.
Makes sense? Okay. So I've used 6 of my 24 electrons. Then if I go ahead and dot, 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 there's another 6. Another 6. That gets me to 24. Am I good? I am. What? I'm good because aluminum is one of the 4 atoms that we talked about that have exceptions. So the exceptions for aluminum and boron is they only want 3 bonds, so they only want to see 6 electrons. And the exceptions for phosphorus and sulfur where they can accept more than 8 electrons. So that's the Lewis structure for aluminum chloride. What's the 3D structure look like? So it doesn't exist, right?
Oh, yeah.
There is no 3D structure for this molecule. It's only 2D. So all you could do for this one is say put aluminum there and then put the chlorines at 180 degrees away from each other, and now I've got a trigonal planar structure. So what's the Vesper structure? There isn't one. Not applicable. Reasoning it's not applicable? There are no lone pairs of electrons on the aluminum, which is the central atom. So the structure is not modified. So it's just trigonal planar. Okay. We didn't get a chance to talk about the anomaly with the next one, but do we know what it is? How's this one different than any of the other ones that we've talked about so far? There's 2 central atoms. There's a carbon. Oh, we should just start this from scratch. So there's 4 here. There's 3 electrons here. There's 6 electrons here. There's another electron here. So what are we looking at? 14 total electrons. So I'm going to put carbon, hydrogen, 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 oxygen, hydrogen. How come that's got to be the structure?
Because carbon can make 4 bonds, oxygen can do 2, and the rest of them can do 1.
There is only one way to do it. Carbon can make 4 bonds, oxygen can make 2, and hydrogens can only make 1. This is the only way it works. If you put stuff anyplace else, like a double bond between the oxygen and the carbon, you don't have enough links to attach all the hydrogens. This is the only way it works. Okay, so I haven't used all the electrons. I'm missing 4. So where do they go?
On the oxygen.
On the oxygen. So I'll put 1, 2, and then 3, 4. All right, so I have 2 central atoms. This is a central atom, and this is a central atom. So you need names for both of them. So first off, what's the 3D going to look like for this? Around every bond, 2 of the things connected to the central atom are going to be in the same plane. Okay, so I'm going to start off with this hydrogen right here. So that hydrogen is right there. And what is it connected to? A carbon. So I'm going to say that those guys are in the same plane. And then what's that carbon also connected to? An oxygen. I'm going to say that's in the same plane. And then what's that oxygen connected to? A hydrogen. So those 4 atoms if I took them out of the structure, they would lay down on a piece of, on a table perfectly flat. They're all in the same plane. I have to deal with 4 more things. So the first thing I need to deal with are the hydrogens on the carbon. So I'm going to draw dash, 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 H. So that hydrogen is back there behind. Then the other one is a wedge. So that one's coming out at you. So what's the shape around that carbon? Tetrahedral. How many things are connected to it? 4. And so 4 things connected to the central atom means tetrahedral. How many things are connected to the oxygen? Don't get tricked. There are 4 things connected to the oxygen. I know I'm a very poor drawer, but can we tell what's going on with the oxygen? How many things are connected to the oxygen? 4. There's a carbon and a hydrogen and 2 sets of lone pairs. Those sets of lone pairs take up position just like an atom would take up position. So that oxygen is seeing 4 things around it, and so that shape is a tetrahedral. So that's what we're looking at. A tetrahedral shape connected to a tetrahedral shape. So this guy is in its, well, let me do it over here. Let's say oxygen, I'll put it up top since I don't have any space, carbon and oxygen. And then there's a Vesper and there's a molecular, and a Vesper and a molecular. Does that make sense? So what's the Vesper shape around the carbon? There isn't one because there are no lone pairs around the carbon. What's the Vesper shape around the oxygen? Tetrahedral. What's the molecular shape around the carbon? And molecular shape around the oxygen? Bent. That's it. Does interesting things to this molecule. Does anybody know what this one is? The name of this CH3OH? This is methanol. We talked about this in 121. Do you remember what I said about it? Anybody? Properties of methanol? Methanol sounds a heck of a lot like what? Ethanol. So obviously you can drink ethanol. What happens if you drink methanol? You die. Your liver turns off. Our bodies cannot metabolize it, and so or metabolize it in a safe fashion. And since it's too dumb to not metabolize it, it metabolizes it into a toxin. It says, that shouldn't be here. Let me make something out of it. Well, that was a bad idea, and it made something worse. But it just keeps doing it until you die. So this molecule, tell me about the ability of these guys to mix with water. The first one's a trick question. It's an ionic substance, so yes, it's a soluble ionic substance, so that will definitely dissolve in water. How about the next one? It is soluble. You're incorrect. Hydroxides are what make insoluble things soluble. So why is this thing soluble? For you to have, so when we're talking about mixing with water, what's water's polarity? Is it polar or non-polar? Polar. Water's polar. So if water mixes with ethanol or methanol, methanol must be polar. So how is this molecule polar? How do you get something, how do you get a bond to be polarized? What was the key to having something to be polar?
The differences in the electronegativity of the atoms.
Has to be greater than 0.5. So what's the difference in electronegativity between the carbon and the hydrogen? It's 0.3. So this entire portion of the molecule doesn't care to be anywhere near water. That is non-polar. But what about the other side of the molecule? What's the charge on the oxygen, or the oxidation state on the oxygen? It's 3.5. Sorry, not the oxidation state, but the electronegativity. And the electronegativity on the hydrogen, it's 2.2. That's a huge difference. So what we have here is, right on top of the oxygen, I've got a pretty powerful partial negative. And on the hydrogen, I've got a pretty powerful partial positive. That side of the molecule loves water. Who wins? That side of the water. Sorry, that side of the molecule is powerful enough to mix with water. Do you think there's a point where so this is one carbon with a hydroxyl group, and that's polar. What happens if I put 2 carbons on and have a hydroxyl group? Is it still polar? That molecule is called ethanol. We know it's polar, right? You mix 50% water and ethanol in class. Plus, it's in beer and wine. And if it wasn't polar, it'd sit on top of it like oil sits on top of vinegar and salad dressing. So we know that's polar. 3 of them, that's rubbing alcohol. 3 carbons on a hydroxyl group, does that mix with water? Yep. You can only buy like a 70% solution. So the other 30% is water. What about 4?
Is that like isopropyl alcohol?
Isopropyl alcohol, rubbing alcohol. It's 3 carbons in a row with the alcohol group coming off the middle instead of coming off the end.
So when you have 90% isopropyl alcohol, then it's only 5% water then?
You said what?
95%?
Yeah, it's 5% water. That stuff is tight? That stuff kills lots of things and causes your skin to dehydrate so fast that if you don't get something on it right away, it'll chap. It'll crack. I mean, if it's your hands, it'll just crack open. If it's anything more sensitive, like your face, it'll just crack open. So if you touch high concentration isopropyl alcohol, get some lotion on even like a chapstick, like rub it on it. That'll protect it from splitting open. The splitting open part's terrible, right? Largest organ in your body exposed to the atmosphere, bacteria and whatnot. Don't want that. Okay, so this guy's definitely going to mix with water. When we get to 5 carbons and just 1 hydroxyl group, that's when it starts to not want to mix with water. So there'll be a point where I have so much stuff that hates water that the molecule will not mix. Kind of a balancing act. Formal charge on each atom in the methanol molecule. All right, so what about the hydrogens? What do we got here? Formal charge on the hydrogens. It has 1 valence electrons, minus 0 lone pairs of electrons, minus 1/2 of the bonding electrons, which is 2 divided by 1, so it's 0 for all of those. So nature really likes it when the formal charge on a molecule or on an atom in a molecule is 0. That makes it very, very stable. All right, what about the carbons? So I got a carbon here. It has 4 valence electrons. It has no lone pairs of electrons on it, and it has 8 electrons divided by 2 gives us, oh, imagine that, a 0. So again, nature loves that. Can you tell me what the oxygen's formal charge is going to be?
0.
Has to be 0 because this is a neutral molecule, so there's no way it can be anything other than 0. But let's do the math anyway. So oxygen has 6 valence electrons. It has 4 lone pairs of electrons, and it has 4 electrons that are in bonds divided by 2 gives you 0. So formal charges work out on that. Methanol stable electronically. All right, what's the specific heat of a piece of metal that gains 4.5 kilocalories of energy and mass of 1250, starting temp is 68 degrees? That was not nice. This problem will give you different answers if you do the math differently. All right? That doesn't sound like it should be possible, but it totally is. What am I talking about?
If you convert Fahrenheit before you So I don't know, I guess, yeah, you convert the Fahrenheit now and then subtract them to get your change in temp, or you do it in Fahrenheit and then then you convert your
Answer.
answer from the change in temp to Celsius.
Yep. That is exactly right. What are we concerned about with this problem, with the change in temperature? What do we want to know?
What is Celsius?
I want to know what the change in temperature is in Celsius. So what I need to do is figure out what the change in temperature is, and then convert that into Celsius. That's how the problem is done. So I have 750 degrees. I'm going to subtract off 68 degrees, and I'm going to get 686. Is that right? Yeah? Was it 86? Oh, 82. I'm an idiot. Yeah, 682 degrees Fahrenheit. That's my change in temp. So that's the magnitude of the change in temperature. And so now I need to figure out what that magnitude would be in the Celsius scale. So I subtract off 32, put that in parentheses, and then I multiply by 5/9. So I'm at 682 minus 32, then hit equals times 5 divided by 9. So that's super important that if you're punching this into the calculator, that you make sure those parentheses are around, you do the subtraction, hit enter, or put parentheses around it, then hit times 5 divided by 9. Otherwise, it's going to do this and then subtract off the product of that. Everybody good with that? All right, so I've got, click it, 361 degrees Celsius. Okay, so it's Q equal, well, I don't even need to do that. What are we looking for this problem? I'm looking for C, and so that's specific heat, and C's units are calories or joules divided by grams and degrees C. So I just need to set it up so I get those numbers. So I'm going to put 4500 calories here. I just got rid of the K and just turned it into calories right off the bat. Then I'm going to go ahead and divide by 1250 grams, and I'm going to divide by 361 degrees Celsius. And so we end up with 4500 divided by 1250 divided by 361. I get 0.00997 calories gram degrees C. So really low specific heat. I only have 2 sig figs, so that would be 0.010 calories per gram degrees C. Which atoms are able to violate the octet rule? Okay, so we've got boron and aluminum want 6 electrons, and we've got phosphorus and sulfur can have more than 8 electrons. That's it. Is this violation a certainty or just a possibility? The boron and aluminum is a must. It's always going to have just 6 electrons. The sulfur and the phosphorus are, if I have to take them, I'll take them. But I don't really want to. But I will.